Welcome to our channel, fellow explorers of the cosmos. Today we embark on a journey to the most tantalizing frontier of space exploration, interstellar travel, at speeds approaching the cosmic speed limit, the speed of light. For centuries the stars have beckoned us with their distant light, whispering tales of uncharted territories and celestial wonders. Yet the vast gulf between them and us has remained a seemingly insurmountable obstacle. Even with our fastest spacecraft, reaching the nearest star would take tens of thousands of years, a timescale that dwarfs the entirety of human civilization. But what if we could unlock the secrets to traveling at a significant fraction of the speed of light? Could we finally reach out and touch those distant stars, setting foot on exoplanets orbiting alien suns? Before we contemplate near-light-speed travel, we must grasp the sheer immensity of the cosmic arena. Our galaxy, the Milky Way, is a swirling island of hundreds of billions of stars, stretching over 100,000 light-years across. To put that into perspective, 1 light-year is the distance light travels in a year, moving at a staggering 186,000 miles per second. The nearest star system to our own, Alpha Centauri, is a mere 4.37 light-years away. The Voyager 1 probe, the fastest human-made object, would still take over 70,000 years to reach Alpha Centauri. The distances are so vast, the timescales so long, that even contemplating a journey to another star seems almost unfathomable with our current technology. For decades, scientists and science fiction writers alike have dreamt of harnessing the power of nuclear fusion to propel us across the interstellar gulf. Fusion, the process that powers the sun, involves fusing lighter atoms like hydrogen into heavier ones like helium, releasing tremendous amounts of energy. Imagine a spaceship equipped with a fusion reactor, a miniature sun blazing away in its core. This reactor would heat up a propellant like hydrogen to millions of degrees, transforming it into a superheated plasma. This plasma would then be channeled through magnetic nozzles, generating thrust that could propel a spacecraft to a significant fraction of the speed of light. With fusion propulsion, journeys to nearby stars could be reduced from tens of thousands of years to mere centuries or even decades. Now let's delve into the realm of antimatter, a substance as perplexing as it is powerful. Antimatter is like the mirror image of ordinary matter. For every particle of matter, like an electron, there exists an antiparticle with the same mass, but the opposite charge, in this case a positron. When matter and antimatter collide, they annihilate each other in a burst of pure energy, unleashing the most efficient conversion of mass to energy allowed by Einstein's famous equation, E equals mc squared. A spacecraft powered by antimatter could, in theory, achieve speeds approaching a significant fraction of the speed of light. Producing and storing antimatter is incredibly difficult and expensive. Despite these hurdles, the potential of antimatter propulsion is too alluring to ignore. Imagine fleets of tiny spacecraft, unburdened by fuel tanks, setting sail for distant stars propelled by the pressure of light. This is the vision of laser-pushed light sails, straddling science fiction and reality. Picture a spacecraft with a vast, ultra-thin reflective sail. A powerful laser beam from Earth or orbit focuses on this sail. Photons strike the sail, transferring momentum, pushing the spacecraft forward. This push could accelerate a light sail to a fraction of the speed of light. Breakthrough Starshot aims to send tiny probes to Alpha Centauri. Despite challenges, laser-pushed light sails are an enticing concept for interstellar travel. Let's venture now into the realm of science fiction, or perhaps science future, where the very fabric of space-time is manipulated, allowing for faster-than-light travel. I'm talking about warp drives, a concept that has captivated the imaginations of science fiction enthusiasts for decades. The idea, first popularized by the Star Trek franchise, involves creating a warp bubble around a spacecraft that distorts space-time, compressing it in front of the ship and expanding it behind. In this warped region of space-time, the spacecraft could effectively travel faster than light without violating Einstein's theory of relativity. However, the concept of a warp drive faces significant theoretical and practical challenges. One major hurdle is the requirement for exotic matter, a hypothetical substance with negative mass-energy density. Despite these hurdles, the allure of warp drives remains strong. Now let's delve into one of the most mind-bending consequences of traveling at speeds approaching the speed of light, time dilation. This phenomenon, predicted by Einstein's theory of special relativity, dictates that time is not absolute but rather relative to the observer's frame of reference. As a spacecraft approaches the speed of light, time slows down for those on board relative to observers on Earth. To illustrate this concept, imagine two identical clocks, one on a spacecraft traveling at a significant fraction of the speed of light, and the other remaining stationary on Earth. As the spacecraft accelerates, those on board would observe their clock ticking at a normal rate. However, from the perspective of observers on Earth, the clock on the spacecraft would appear to be ticking slower. A journey that might take decades from the perspective of those on board the spacecraft could correspond to centuries or even millennia passing on Earth. As we venture further into the realm of interstellar travel at near-light speeds, we encounter a seemingly insignificant yet potentially deadly obstacle: interstellar dust. These tiny particles, scattered throughout the vast expanse of space, pose a significant threat to spacecraft traveling at relativistic speeds. At such speeds, even minuscule dust particles would impact with the force of a bullet, potentially causing significant damage to the spacecraft's hull, instruments, and even jeopardizing the lives of those on board. To protect against this cosmic barrage, interstellar spacecraft would need to be equipped with robust shielding or utilize innovative technologies like magnetic deflectors. These deflectors would create a magnetic field around the spacecraft, repelling charged particles and diverting them away from the ship's path. Shielding would involve layering the spacecraft's hull with materials capable of absorbing or deflecting the high-energy impacts of interstellar dust. As we contemplate the mind-boggling speeds required for interstellar travel, we inevitably confront the daunting challenge of energy. Accelerating a spacecraft to a significant fraction of the speed of light demands an astronomical amount of energy, far exceeding our current capabilities. To put this into perspective, consider that accelerating a spacecraft to 99% the speed of light would require an amount of energy equivalent to the total energy output of the Sun for several years. Harnessing such vast amounts of energy would require breakthroughs in energy production, storage, and conversion technologies. We might need to develop advanced fusion reactors, capable of generating sustained power output far exceeding anything we can achieve today. Another possibility is antimatter annihilation, which offers the most efficient conversion of mass to energy. As we stand on the precipice of the cosmos, gazing out at the vast tapestry of stars, the dream of interstellar travel beckons us forward. While the challenges are undeniable, the immense distances, the need for revolutionary propulsion systems, the perils of interstellar space, so too is the potential reward. Imagine a future where humanity has transcended the confines of our solar system, venturing out to explore new worlds, encounter new life forms, and unlock the secrets of the universe. This is the future that interstellar travel holds, a future limited only by our imagination and our determination to reach for the stars. Perhaps one day, we will develop propulsion systems capable of warping space-time, harnessing the power of antimatter, or riding the very fabric of the cosmos to our destinations. Or perhaps we will discover entirely new physics, new principles that will revolutionize our understanding of space, time, and the nature of reality itself. Now let's turn the question to you, fellow explorers of the cosmos. Imagine for a moment that the technological hurdles of interstellar travel have been overcome. A spacecraft stands ready, equipped with a revolutionary propulsion system capable of reaching a significant fraction of the speed of light. Its destination a nearby star system harboring potentially habitable planets. But there's a catch. Due to the effects of time dilation, what might seem like a few years on board the spacecraft could translate to decades or even centuries passing on Earth. Would you still choose to embark on this one-way journey into the future? Let us know your thoughts in the comments below. As we conclude our exploration of interstellar travel, one thing remains clear. The quest to reach the stars will challenge, inspire, and transform us. Near light-speed travel may seem distant, but it's a dream worth pursuing, reflecting our deepest aspirations. Breakthroughs in physics and propulsion could make interstellar travel a reality soon. When that day arrives, humanity will embark on a new era of exploration beyond our solar system. What wonders await us among the stars? What mysteries will we unravel? The journey of interstellar exploration will lead us to a deeper understanding of ourselves and the universe.